So my name is Matthias Schweiger. I'm from Pilz, and we had the three tasks: RS4 Radar, RS4 Skin, and the safe position signaling. So let's start with the radar. So in this task, we had to evaluate the radar technology for a new kind of a 3D safety sensor. We always kept in mind to do a safety concept. And radar has advantages in the human versus object recognition. So we evaluate this topic too. And we implemented a ROS and a UPC-UA interface to speak with the RS4 controller. So first of all, we had to learn what to do with the raw point cloud data. So from noisy point clouds, we had to develop algorithms to get clustered and filtered objects like the one on the right. Then we can calculate a center point of intensities. And now with that point, we could calculate the directions and velocities of objects and humans. So the bottom right picture is a small sample application, where at the bottom is a safety application and the point is a human, and we can calculate and see the direction of the movement of the human. So goes the human in the direction of the hazard or not. So here a few results. We tested the sensor with a walking and standing person. So the person walks from 1 to 2.2 to 0.3 and so on, and you see the velocity of the person goes up and down, and you can see the distance to the sensor gets lower. So we demonstrate our radar sensor this time in a white housing at the EMA use case. There it supports the safety and measure some point clouds to the RS4 controller from data sensing. So the next task was the RS4 Skin. This was a safety soft skin for the human-robot collaboration method 4, pressure and force limitation. And the advantage is the fast reaction time. So we started with very simple shapes and tested it in our Pilz manipulator. Then we can see it in the block diagram. We could use a Pilz product to connect the skin and connect the robot or the RS4 controller via output, 24-volt safety outputs. And then we showed the skin in the whirlpool use case. Therefore, we have to examine different soft materials. We had to find the right force threshold to determine the activation force. And we 3D printed the gripper of the whirlpool use case and had to develop the 3D shapes of the skin. So yeah, all right. Then this is the result for the skin. The line on top, it's the force limit of the TS 15066, and the red line is the universal robot without a skin with the internal torque sensors. And if we use a skin, we could run the robot 2 times faster. So because of the fast reaction time, we are able to get a higher robot speed. So we can improve the application in terms of speed and cycle time. So another task was the safe position signaling. That's the name for a solution where we add safe speed and safe position safety functions to a robot manipulator without these safety functions. So the test implementation of the solution was with the Pilz component. So we had the Pilz robot manipulator and a non-safety robot drive. And we added the RSCU, it's named Robot Safe Control Unit, to calculate safe speed and safe position monitoring. So what we did, we had to add a dual channel communication through all the joints and a dual channel encoder architecture to get the position data out of the robot manipulator in a safe way. So we started the hardware based on a safety card for one-axis drives from Pilz, and we developed a new firmware which was adding several safety functions for the axis, like safety limited position and safety limited speed, and for the whole robot, so we can monitor the TCP position or the orientation, the tool orientation of the robot in a safe way. So we had a small demo where the light curtain on the right triggers the monitoring of the robot, and if the robot was moving in the red area, it was moving slow with monitored safe speed in this safe position. If the robot was out of the left, it could run full speed. So I'm at the end, and if you have any questions, feel free to ask.